July 14, 1942, Wright Field, Dayton, Ohio. Lieutenant Colonel Thomas Hitchcock stood in the experimental engine testing facility, watching as technicians prepared to fire up the most significant piece of British engineering ever to cross the Atlantic. The Rolls-Royce Merlin 61, fresh from Derby, England, gleamed under the harsh fluorescent lights like a mechanical jewel. Hitchcock, a former Lafayette escadrille pilot who had shot down 3 German aircraft in the First World War, understood engines. He had spent months in England evaluating British fighter performance, and what he witnessed there had shaken his confidence in American aviation supremacy. British Spitfires and Hurricanes, powered by this elegant liquid-cooled V-12 engine, were outperforming every American fighter at altitude. The Merlin specifications read like poetry to engineers who understood internal combustion: 27 liters of displacement, 2-stage 2-speed supercharger, 1,515 horsepower at 20,000 feet. But numbers told only part of the story. This engine represented 15 years of relentless British engineering refinement, racing heritage from Schneider trophy seaplanes, and combat testing that had saved Britain during the darkest days of 1940. As the Merlin roared to life, its distinctive howl filling the test cell, Hitchcock knew he was witnessing both America's salvation and humiliation. The United States Army Air Forces desperately needed this British engine to make their fighters competitive. But the very fact that America, with all its industrial might, had to license a foreign design represented a stinging admission of technological inadequacy. What neither Hitchcock nor anyone else in that room could have predicted was that America's attempt to copy British excellence would evolve into something far more complex than simple imitation. The Packard Motor Car Company would produce over 55,000 Merlin engines, more than Rolls-Royce ever managed. Yet, in doing so, they would discover that copying genius was far harder than creating it, that mass production demanded compromises that diminished performance, and that British engineering philosophy and American manufacturing culture were fundamentally incompatible. The story of how America copied Britain's greatest aero engine and still somehow fell short is a tale of pride, pragmatism, and the collision between craftsmanship and mass production. It reveals that, in war, as in engineering, there are no simple victories, only trade-offs between perfection and practicality. The crisis began in the summer of 1940 when the Battle of Britain demonstrated the Merlin's supremacy beyond any doubt. Royal Air Force pilots flying Spitfires and Hurricanes faced the Luftwaffe's best, the Messerschmitt 109, and survived through a combination of courage, tactics, and superior power at critical altitudes. The Merlin's 2-stage supercharger, developed through years of British research into high-altitude performance, gave RAF fighters a decisive advantage above 20,000 feet. While German engines gasped for air in the thin atmosphere, Merlins maintained their power output through mechanical wizardry that forced compressed air into cylinders with remarkable efficiency. American observers watching from the sidelines recognized a disturbing truth. The United States possessed no equivalent technology. The Allison V-1710, America's primary liquid-cooled fighter engine, produced excellent power at low altitudes but suffered catastrophic performance degradation above 15,000 feet. It lacked the complex 2-stage supercharging that made the Merlin exceptional. The Curtiss P-40 Warhawk, powered by the Allison, could not compete above 20,000 feet. The Bell P-39 Airacobra, another Allison-powered design, was relegated to ground attack roles because of altitude limitations. The Republic P-47 Thunderbolt required a massive turbo supercharger installation that added weight and complexity. America's fighter force faced obsolescence before it even entered combat. In September 1940, the British Purchasing Commission approached Packard Motor Car Company with an audacious proposal. Would Packard be willing to manufacture Rolls-Royce Merlin engines under license for British use? The initial order called for 9,000 engines, an unprecedented peacetime commitment. Packard's president, George Christopher, faced a momentous decision. His company had built luxury automobiles since 1903, earning a reputation for precision engineering and quality. The Packard Twin Six had pioneered the V12 configuration in American cars, but aircraft engines represented an entirely different challenge. Rolls-Royce sent a complete Merlin 20 engine to Detroit in October 1940, along with manufacturing drawings that filled 50 packing crates. When Packard engineers examined the documentation, they discovered their first major obstacle. British drawings used imperial measurements thousandths of an inch, but followed different conventions than American practice. More critically, many components had tolerances specified as limits rather than dimensions plus or minus. The cultural clash began immediately. British engineering drawings assumed craftsmen would hand-fit components to achieve proper clearances. American mass production demanded interchangeable parts that could be assembled without custom fitting. Jesse Vincent, Packard's chief engineer, recognized that direct copying was impossible. The engine would need to be completely redrawn to American standards. Between November 1940 and May 1941, Packard engineers created 5,000 new drawings, converting every British specification to American equivalents. In doing so, they made their first compromises. Some British tolerances were loosened to permit faster manufacturing. Others were tightened where American tooling could achieve better precision than British methods. The supercharger represented the greatest challenge. Rolls-Royce's two-stage unit incorporated years of proprietary research into impeller design, diffuser geometry, and intercooling. The tolerances were extraordinarily tight, measured in 10,000ths of an inch. Any deviation affected performance. Packard metallurgists encountered another problem. British specifications called for materials that had no American equivalent. Special aluminum alloys, proprietary steels, even the fuel system components required materials unavailable in the United States. Substitutions were necessary, each one potentially affecting performance. The first Packard-built Merlin, designated the Packard V1650, ran on the test stand in August 1941. It produced 1,300 horsepower at 3,000 revolutions per minute, matching the British Merlin 28's output. Company officials celebrated. The American copy had equaled British performance, but celebrations proved premature. When the first production engines reached 500 hours of testing, failures emerged. Connecting rods cracked, supercharger bearings seized, cylinder heads developed cracks around exhaust ports. The problem stemmed from metallurgical differences and manufacturing variations that hadn't appeared in the prototype. British engines were assembled by craftsmen who spent years learning their trade. At Rolls-Royce's Derby plant, individual fitters worked on engines from start to finish, personally responsible for quality. They hand-selected bearings for perfect fit, adjusted valve clearances by feel, and balanced connecting rods to eliminate vibration. Packard's mass production approach employed semi-skilled workers who performed single, repetitive tasks. Quality depended on tooling precision and statistical process control, not individual craftsmanship. This philosophical difference would haunt the Packard Merlin throughout its production life. By December 1941, when America entered the war, the stakes had risen exponentially. The United States Army Air Forces needed Merlin engines for the P-51 Mustang, which had been designed around the British engine. The Royal Air Force needed Packard production to replace combat losses and equip new squadrons. Failure was unacceptable. Colonel Hitchcock, now assigned to accelerate Merlin production, pushed Packard relentlessly. Production climbed from 30 engines monthly in January. 1942 to 100 by June. But quality problems persisted. Approximately 15% of engines failed acceptance testing compared to 3% for British-built Merlins. The differences were subtle but significant. Packard Merlins developed slightly less power at altitude. Fuel consumption was marginally higher. Engine life between overhauls averaged 50 hours less than Rolls-Royce engines. These weren't catastrophic failures, but they represented measurable shortfalls in performance. American pilots flying Packard Merlin-powered P-51 Mustangs in combat discovered the differences quickly. The engine ran hotter than British versions. Oil consumption was higher. Some pilots reported roughness at high manifold pressures that British Merlins didn't exhibit. Captain Don Gentile of the 4th Fighter Group, a top American ace with 21 victories, flew both British and American Merlin-powered Mustangs. His maintenance reports noted that Packard engines required more frequent oil changes and spark plug replacements. He wasn't complaining. The Packard Merlin was still superior to any other American engine, but the British version was noticeably smoother. If you are fascinated by the untold stories of World War II engineering and want to discover more amazing facts about the technology that shaped history, make sure to subscribe to our channel and hit the notification bell so you never miss an episode where we uncover the secrets behind the machines that changed the world. The root causes of Packard's shortfall lay in manufacturing philosophy. Rolls-Royce accepted that engine production would be limited by the time required for precision handwork. Packard believed mass production methods could overcome any obstacle through volume and standardization. Consider the crankshaft. The Merlin's crankshaft was a masterpiece of metallurgy, forged from special steel, nitrided for hardness, and balanced to eliminate vibration. British craftsmen spent hours balancing each crankshaft individually, removing material until it met specifications. Packard initially attempted to duplicate this process, but quickly abandoned it as too slow. Instead, they invested in precision balancing equipment that could process crankshafts in minutes rather than hours. The equipment worked, but couldn't match the precision of skilled craftsmen. Packard crankshafts were balanced to within 2 grams. British crankshafts were balanced to within half a gram. The supercharger impeller presented similar challenges. This rotating component compressed intake air to maintain sea level pressure at altitude. The impeller's blades had to be precisely shaped and balanced to avoid vibration at 20,000 revolutions per minute. Rolls-Royce cast impellers from aluminum alloy, then hand-finished each blade to exact profiles. Inspectors used optical comparators to verify blade angles to within minutes of arc. The process took skilled workers 3 hours per impeller. Packard attempted to machine impellers from forgings, reducing handwork. The process was faster but produced imperceptible variations in blade geometry that reduced compression efficiency by approximately 2%. At 25,000 feet, this translated to roughly 20 horsepower, less than British equivalents. Magneto-timing represented another subtle difference. The Merlin used 2 magnetos to provide redundant ignition, critical for combat reliability. Timing had to be precisely synchronized to fire spark plugs at exactly the right crankshaft position. British practice involved hand-setting each magneto with specialized fixtures, a process requiring considerable skill. Packard developed automated test equipment that set timing mechanically. The equipment was consistent but slightly less precise than hand methods. The result was barely measurable in testing, but noticeable to experienced pilots as slight roughness under certain operating conditions. By mid-1943, Packard was producing over 400 Merlins monthly, and the United States Army Air Forces depended absolutely on this production. The North American P-51 Mustang, which would become the war's finest long-range escort fighter, existed only because of Packard Merlins. The transformation of the Mustang from mediocre performer to superb fighter demonstrated both the Merlin's excellence and the Packard version's limitations. The original P-51A, powered by the Allison V-1710, was fast at low altitude, but unable to escort bombers above 20,000 feet. In October 1942, Rolls-Royce test pilot Ronald Harker flew a Mustang at Duxford and immediately recognized that installing a Merlin would transform the aircraft. British engineers fitted a Merlin 61 to a Mustang airframe, creating the P-51B. The results exceeded all predictions. The Merlin Mustang could reach 44,000 feet and cruise at 360 miles per hour at 25,000 feet. Range with drop tanks exceeded 2,000 miles, enough to escort bombers to Berlin and back. The combination of American airframe and British engine created the war's most effective escort fighter. But when production Mustangs began receiving Packard V-1657 engines, subtle performance differences emerged. Packard Mustangs were approximately 5 miles per hour slower at altitude than British Merlin Mustangs. Rate of climb was marginally lower, most significantly the critical altitude, where the engine produced maximum power, was about 1,000 feet lower. These differences stemmed from accumulated manufacturing variations. The Packard supercharger's slightly lower efficiency, combined with fractionally higher internal friction and less precise fuel metering, reduced overall performance by 3 to 4%. In absolute terms, a Packard Mustang still outperformed any German fighter. In relative terms, it fell short of British standards. German pilots who encountered Packard Mustangs and British Mustangs couldn't distinguish between them in combat. But meticulous Luftwaffe intelligence officers who examined captured engines noticed the differences. A technical report from Rechlin Test Center noted that the American Merlin exhibited rougher machining, larger manufacturing tolerances, and signs of less careful assembly than British examples. The report concluded the American version sacrifices some performance for production speed. This is consistent with their industrial philosophy of adequate quality in vast quantities rather than excellent quality in limited numbers. Major Erich Hartmann, Germany's top ace with 352 victories, encountered Mustangs over Romania in 1944. In post-war interviews, he recalled, "The American Mustang was formidable, very fast, excellent range, and deadly firepower. I could not tell if I faced an English Merlin or American Merlin. Both were superior to our engines at altitude." This assessment captured the essential truth. Packard's Merlin, despite falling short of British standards, was still world-class. The shortfall mattered to engineers and test pilots, but had minimal impact on combat effectiveness. By 1944, Packard was producing over 600 engines monthly, double Rolls-Royce's output. This quantitative superiority outweighed any qualitative shortfall. The European theater alone required 450 Merlin engines monthly to replace combat losses and equip new squadrons. Packard production made this possible. The price of mass production became increasingly clear as the war progressed. Rolls-Royce Merlins averaged approximately 400 hours between major overhauls. Packard Merlins averaged 350 hours. The difference stemmed from accumulated wear and components manufactured to looser tolerances. British connecting rods hand-fitted to crankshaft journals developed less play during operation. Packard rods, machined to looser tolerances for interchangeability, developed more play, increasing stress and reducing engine life. Valve guides presented similar issues. Rolls-Royce used special cast iron with precise boring to maintain tight clearances. Packard substituted bronze guides that wore faster but were easier to manufacture. The result was increased oil consumption and more frequent valve adjustments. American maintenance crews adapted to these differences by performing more frequent inspections and replacing components earlier. The United States' logistical superiority could support this maintenance-intensive approach. British forces, operating with limited resources, required more durable engines that could operate longer between overhauls. The philosophical divide between British craftsmanship and American mass production extended to every aspect of engine manufacture. Rolls-Royce viewed each engine as a precision instrument requiring careful handwork. Packard viewed engines as industrial products requiring consistent machine work. Neither approach was inherently superior. British methods produced engines of exceptional quality but limited quantity. American methods produced engines of good quality in vast quantities. The war required both. By late 1944, combat reports revealed an unexpected problem. Packard Merlins were failing in combat at slightly higher rates than British engines. The difference was small, approximately 3 failures per 100 combat hours versus 2 for British Merlins, but statistically significant. Investigation revealed that the failures occurred primarily in engines operating at maximum power settings for extended periods. The Packard engine's slightly higher internal friction generated more heat under sustained maximum power, leading to failures of components with marginal cooling. Rolls-Royce engineers visited Packard in November 1944 to investigate. Their report identified the problem, but offered no easy solution. The failures stemmed from accumulated small differences in manufacturing precision. Fixing them would require returning to British standards of handwork, eliminating the production speed advantages that made mass production possible. Colonel Bruce, now Brigadier General Bruce, faced an impossible choice: reduce production to improve quality, or accept higher failure rates to maintain output. The decision was made for him by strategic necessity. The air war over Germany required maximum Merlin production, regardless of quality shortfalls. The compromise solution involved slightly reducing maximum manifold pressure limits for Packard engines. This decreased maximum power by approximately 30 horsepower, but reduced thermal stress enough to bring failure rates down to acceptable levels. Pilots complained about the power reduction, but it was preferable to mid-flight engine failures. This limitation meant that Packard Mustangs operated with approximately 1,470 horsepower at war emergency power, while British Merlin Mustangs could produce 1,500 horsepower for short periods. The 30 horsepower difference was barely noticeable in combat, but represented another measurable shortfall. American test pilots at Wright Field conducted extensive comparison testing between Rolls-Royce and Packard Merlins in identical airframes. Their classified report from March 1945 provided the most detailed analysis of the differences. At sea level, both engines performed identically. At 10,000 feet, performance remained virtually the same. At 20,000 feet, the Rolls-Royce engine produced approximately 20 more horsepower. At 30,000 feet, the difference increased to 40 horsepower. At critical altitude, around 26,000 feet, the British engine's superiority was most pronounced. The report attributed these differences to supercharger efficiency. The Rolls-Royce two-stage supercharger maintained compression ratios across all altitudes more effectively than the Packard version. The differences stemmed from blade geometry variations measured in thousandths of an inch. Fuel consumption tests revealed that Packard engines burned approximately 5% more fuel at cruise power settings. This reduced the Mustang's range by roughly 100 miles at maximum radius. Mission planners had to account for this difference when calculating escort capabilities. Engine life testing showed that Rolls-Royce Merlins ran smoother throughout their operational life. Packard engines developed more vibration after 200 hours of operation, indicating greater wear in rotating assemblies. This vibration could fatigue airframe components and reduce cockpit comfort. Despite these measured shortfalls, the test pilot's conclusion was unambiguous. The Packard Merlin is an excellent engine that enables the P-51 to perform its mission effectively. While the British engine exhibits superior performance in several parameters, the Packard engine's advantages in availability and cost-effectiveness outweigh its technical limitations. This pragmatic assessment captured the essential paradox. America had copied Britain's best engine and fallen short of British standards, yet the copy was good enough to help win the war. Production statistics told the quantitative story. Between 1941 and 1945, Rolls-Royce and its licensed manufacturers in Britain produced approximately 32,000 Merlin engines. Packard produced 55,523 engines in the same period. This numerical superiority came at a cost. Packard's engines averaged 350 hours between overhauls compared to 400 for British engines. They consumed more fuel, produced slightly less power at altitude, and required more maintenance. But there were 55,000 of them. The unit cost difference was equally striking. A Rolls-Royce Merlin cost approximately £9,000 sterling to manufacture, roughly $45,000 in 1944 values. A Packard Merlin cost $13,500. American mass production achieved a 67% cost reduction, despite paying higher labor rates. This cost advantage enabled the United States to equip 15 fighter groups with Merlin Mustangs, plus supply British, Canadian, Australian, and other Allied forces. Without Packard production, the strategic bomber offensive over Germany would have been unsustainable. The human dimension of the quality shortfall affected pilots who flew both versions. Squadron leader James Johnson, the Royal Air Force's top-scoring fighter pilot with 34 victories, flew both British and American Merlin-powered Mustangs. His assessment was characteristically blunt. The Packard Merlin is a good engine, competent and reliable. The Rolls Merlin is a great engine, refined and powerful. In combat, the difference rarely matters. Both will get you home if you don't push them beyond limits. But the Rolls feels like a thoroughbred. The Packard feels like a workhorse. American pilots generally couldn't tell the difference because most never flew British Merlin aircraft for comparison. Captain Chuck Yeager, who became America's first ace in a day with 5 kills on October 12, 1944, flew Packard Merlin Mustangs exclusively. In post-war interviews, Yeager said, "I never had problems with the Packard Merlin. It was strong, reliable, and powerful. I didn't know there was a difference until after the war. If the British version was better, it couldn't have been by much." The Packard Merlin won the air war over Europe. This assessment from one of America's greatest pilots illustrated how the shortfall's significance depended on perspective. Engineers saw measurable performance differences. Pilots saw an engine that enabled them to accomplish their missions. The final irony emerged in the war's closing months. Rolls-Royce developed the Merlin 100 series with improved superchargers, producing 1,700 horsepower. These engines powered the fastest piston engine fighters ever built, including the Spitfire 21 and the de Havilland Hornet. Packard attempted to license the advanced version, but encountered insurmountable problems. The 100 series Merlin incorporated manufacturing techniques that were simply incompatible with American mass production methods. The supercharger alone required hand fitting that Packard's production lines couldn't accommodate. The United States Army Air Forces briefly considered ordering limited quantities of British-built 100 series Merlins for special operations units. But by early 1945, jet engines were clearly the future. Resources were redirected to jet development rather than perfecting piston engine technology. If you want to dive deeper into how American and British engineering philosophies clashed and collaborated during World War II and discover more incredible stories about the hidden battles fought in factories and design offices, subscribe now and join thousands of history enthusiasts who are uncovering the real stories behind the machines that won the war. The Packard Merlin continued in production through September 1945. The final engine, number 55,523, came off the assembly line on September 6th. 8 days after Japan's surrender. It was installed in a P-51D and flown to storage at Ontario Army Airfield in California, where it remained until being scrapped in 1949. Post-war analysis by the United States Strategic Bombing Survey examined whether the Packard Merlin's shortfall had affected combat outcomes. The survey's conclusion was unequivocal. While the Packard engine exhibited measurable performance deficiencies compared to British-manufactured Merlins, these differences had negligible impact on combat effectiveness or mission success rates. The survey noted that the Packard Merlin's most significant contribution was not its performance, but its availability. The engine's mass production enabled the United States to field sufficient fighter forces to achieve air superiority over Europe. Without Packard production, the strategic bombing campaign would have failed regardless of how good British Merlins were. This strategic perspective reframed the entire question of whether America fell short. In absolute engineering terms, yes, the Packard engine was inferior to the Rolls-Royce original. In strategic terms, no, because it existed in numbers that made victory possible. British engineers who examined the Packard Merlin program after the war offered mixed assessments. Some admired American manufacturing prowess and production volume, others lamented the compromises necessary to achieve that volume. Stanley Hooker, who designed the Merlin's supercharger, visited Packard in 1946. His report acknowledged American achievements while noting quality sacrifices. The Americans accomplished something we could not, producing Merlins in vast quantities at reasonable cost. However, their engines lack the refinement and reliability of Derby production. This is the inevitable consequence of choosing quantity over quality. Hooker's assessment was accurate but incomplete. Packard hadn't simply chosen quantity over quality. They had discovered that copying British quality using American methods was impossible. The gap between British craftsmanship and American mass production was unbridgeable without fundamentally changing one approach or the other. The metallurgical differences illustrated this point perfectly. British Merlins used materials specifically developed for aircraft engine applications, proprietary alloys with precise compositions. Packard had to substitute available American materials, which were good but not identical. Connecting rod bolts provided a specific example. Rolls-Royce specified a special steel with specific tensile strength and fatigue resistance. Packard substituted SAE 4640 steel, the closest American equivalent. Laboratory testing showed the Packard material had 96% of the British steel's fatigue strength. In absolute terms, 96% was excellent. In relative terms, it was 4% inferior. Multiply this 4% shortfall across dozens of components, and the cumulative effect explained why Packard engines fell short of British standards. The bearing materials presented similar challenges. Rolls-Royce used a proprietary copper lead alloy for main bearings developed through years of racing experience. Packard couldn't obtain this material and substituted a standard Babbitt alloy. The substitution worked but wore faster under high loads. These material substitutions, individually minor, collectively reduced engine life and slightly increased friction. British engines ran smoother and lasted longer, partly because of superior materials, not just superior manufacturing. The cooling system revealed another subtle difference. The Merlin's liquid cooling system was exquisitely designed to maintain precise temperature control. The thermostat, radiator, and coolant pump worked together with minimal margin for error. Packard's mass-produced cooling components had slightly larger tolerances. Thermostats opened at temperatures varying by plus or minus 3 degrees Celsius instead of plus or minus 1 degree. This variation meant some engines ran slightly hotter, accelerating wear on temperature-sensitive components. Fuel metering presented the most complex challenge. The Merlin used SU carburetors, sophisticated instruments that precisely metered fuel across all operating conditions. These carburetors were hand-calibrated at the factory, a process requiring skilled technicians and specialized equipment. Packard initially attempted to duplicate the hand calibration process, but found it incompatible with production volumes. They developed automated calibration equipment that processed carburetors in 15 minutes instead of 2 hours. The automated process was consistent but less precise than hand methods. The result was fuel-air ratios that varied by plus or minus 2% instead of plus or minus 0.5%. This variation caused some engines to run slightly rich, wasting fuel, while others ran slightly lean, generating more heat. British engines with hand-calibrated carburetors ran closer to optimal mixtures throughout their operating range. By 1946, when the final assessment of the Packard Merlin program was completed, the verdict was clear. America had successfully copied Britain's greatest aero engine and produced it in numbers that helped win the war. But the copy fell short of the original in measurable ways that stemmed from fundamental differences in manufacturing philosophy. The shortfall wasn't failure. It was the inevitable consequence of prioritizing production volume over individual unit perfection. Packard made the right strategic choice. The war required 55,000 engines, not 32,000 perfect ones. The legacy of the Packard Merlin extended far beyond World War II. The production techniques developed to mass produce complex aircraft engines became the foundation for America's post-war aviation industry. The lessons learned from attempting to copy British craftsmanship shaped American engineering education for decades. Engineering schools began teaching that seemingly simple tasks like copying existing designs involved hidden complexities. Materials, tolerances, manufacturing methods, and quality control all affected final performance in ways that weren't obvious from drawings or specifications. The Packard Merlin program also demonstrated that national industrial cultures couldn't be easily transplanted. British craftsmanship traditions, stemming from centuries of precision manufacturing, required skills and attitudes that couldn't be replicated in American factories, organized around different principles. This cultural incompatibility explained why direct copying failed and adaptation was necessary. Packard didn't simply copy the Merlin. They created an American version that looked similar but embodied different manufacturing assumptions. In retrospect, the question of whether America fell short by copying Britain's engine contains a false premise. Packard never truly copied the Merlin. They adapted it, translated it from British to American industrial language, and in doing so created something that was simultaneously inferior and superior. Inferior in individual unit performance, superior in aggregate contribution to victory, inferior in precision and refinement, superior in cost-effectiveness and availability, inferior in meeting absolute engineering standards, superior in meeting strategic military requirements. The Packard Merlin story teaches that in complex endeavors like war, there are no simple metrics of success. The best engine isn't necessarily the one with the highest performance, but the one that best serves strategic needs. Packard understood this even if their engines never quite matched British standards. 55,000 Packard Merlins powered the Allied victory in Europe. They weren't perfect copies of British excellence, but they were good enough in sufficient numbers. Sometimes in war and in engineering, good enough in quantity beats perfect in scarcity. The final assessment belongs to Sir Stanley Hooker, who created the Merlin supercharger and understood the engine better than perhaps anyone alive. In his 1984 autobiography, Not Much of an Engineer, Hooker wrote about Packard's achievement. The Americans took our design and made it their own. They couldn't match our manufacturing standards, so they changed the design to suit their capabilities. This took more intelligence and courage than simple copying would have required. They fell short of our standards, but succeeded in their mission. That is engineering triumph, not failure. Hooker's generous assessment captured the essential truth about America's copying of Britain's engine. The shortfall was real, measurable, and inevitable, but it didn't matter. What mattered was that 55,000 engines rolled off Packard's production lines and into Mustangs that escorted bombers to Berlin, fought for air superiority over France, and helped win the war in Europe. The Packard Merlin wasn't the equal of the Rolls-Royce Merlin. It didn't need to be. It just needed to be good enough in sufficient quantity at the right time. On all three counts, it succeeded brilliantly. America copied Britain's engine and fell short of British standards. But in falling short, they achieved something Britain couldn't: mass production of a world-class engine at a price and pace that strategic necessity demanded. The copy was inferior, but there were 55,000 of them. In the mathematics of total war, quantity has a quality all its own. The Packard Merlin proved this axiom beyond doubt, demonstrating that sometimes the best answer isn't perfection, but adequacy in abundance. The British crafted excellence. The Americans manufactured sufficiency. Together, they powered victory. The Merlin's dual nationality, British designed and American built, symbolized the alliance that won World War II. Neither nation alone could have prevailed. Together, they were unstoppable. The engine that powered this partnership was simultaneously Britain's finest achievement and America's successful adaptation. That it fell short of original standards while helping win the war perfectly captures the paradox of Allied cooperation: imperfect, complicated, sometimes frustrating, but ultimately triumphant. 55,000 Packard Merlins stand as testament to American industrial power and its limitations. They couldn't quite match British excellence, but they could mass-produce competence. In 1942 through 1945, competence in quantity was exactly what victory required. The story of why America copied Britain's engine and still fell short is ultimately a story about different paths to the same destination. Britain sought perfection through craftsmanship. America sought sufficiency through production. Both succeeded in their own way, and together they created the engine that powered Allied victory in the skies over Europe. The Rolls-Royce Merlin was the finest piston aero engine ever built. The Packard Merlin was the most successfully mass-produced version of excellence ever attempted. Neither could have won the war alone. Together, they powered 15,000 Mustangs that achieved air superiority, destroyed the Luftwaffe, and helped bring the Third Reich to its knees. That is not falling short. That is triumph through imperfect but sufficient means, the very definition of strategic success in total war.